Okay, so we were studying speed torque characteristics of DC shunt motors under braking conditions. You can see my screen. Yes.
Yes, sir.
So if you
Yes,
remember,
sir.
these were the speed torque characteristics under motoring conditions for different values of armature circuit resistance. This one we had taken as the natural characteristic, and these characteristics were with increasing values of external resistance inserted in the armature circuit. Then we had seen that with the supply voltage held constant, regenerative braking is possible only with an active load. That means a load that will drive the motor to a speed greater than its no load speed. And under this condition, these were the speed torque characteristics under regenerative braking conditions. So the operation shifted from the first quadrant to the second quadrant. Motor speed is still positive, but the torque is negative. So your motor power becomes negative. That means instead of absorbing power, the motor now starts delivering power back to the supply. Then we had seen that for rheostatic braking or dynamic braking, the supply across the field is held constant, whereas the armature is disconnected from the supply and connected across an external rheostat. That is why it is also known as rheostatic braking. So V becomes 0. So these were the speed torque characteristics, the red color ones. These were the speed torque characteristics under rheostatic braking. Okay. Operation in the second quadrant, the motor is still generating power, the power is still negative, the motor is delivering power, and that power is dissipated in the external rheostat. The third condition we had seen was plugging, in which the supply across the field was held constant, just like under motoring, but the armature connections were reversed, so that your V becomes negative. And your armature current IA becomes negative of V plus E upon R. And these were the characteristics, as we had seen, the green lines. These were the characteristics under plugging or counter current braking. Okay. All characteristics under plugging will still have the same y-intercept, but that y-intercept is now negative instead of positive. And so we had seen that in case of plugging, suppose the motor is operating at this point, as soon as we reverse the armature terminals, the operation shifts to this characteristic and then moves along this line. And when the speed becomes 0, the torque is negative. So if we do not disconnect the supply, the motor starts rotating in the reverse direction. Till here we had studied in the previous class before the exam last Tuesday. And then I had asked you that there is one more case where you can get plugging, even without reversing the, what do you say, armature terminals. What is that case? I had asked you, nobody had answered. Correct? Now, do you have the answer to that question now? Yes, does anybody have the answer now? Yes or no?
Sir, if we rotate the motor in opposite direction of the load torque,
We rotate the motor in opposite direction to the load torque. Opposite direction to the load torque. Anyone else?
Sir, by changing the IF value means field, if we reduce the field, then means EMF will be more than V. Means it will move in the reverse direction.
If you reduce the field, the EMF will also reduce.
EMF will also
Proportional to flux
increase.
and speed.
Yes, yes.
E is proportional to flux and speed. If you reduce the flux, E also reduces.
So means if I will, okay. Here we just want E should be more than V. Then IA will reverse.
Yes. How to make E more than V?
Oh, that's why.
Okay. There are two cases here. One case you've already seen that we had reversed armature terminal so that your V became negative. So your current becomes negative of V plus E divided by R. Correct? This is the case that we had seen. Another possibility is this is the other possibility. Okay. You see the difference? What is the difference? What is the difference? Suman, क्या difference है?
Sir, here I is positive, sir.
I is positive, but the polarity of
E is polarity of
yes, polarity of E is reversed.
E.
Polarity of E is reversed. How is that possible? How can you reverse the polarity of E? How can you
Sir,
reverse
if
the
we
polarity
rotate the
of
motor
E?
in opposite direction,
Yes. How will you rotate the motor in opposite direction without changing the supply? Without changing the supply.
and
So the answer is
so if we apply some force like gravitational force,
suppose this is the value of load torque and we're operating this motor, what we say, let us say it is a crane, okay, that has to lift the load upwards. And suppose this is the value of load torque, okay, and this, let us say this is the characteristic on which the motor is operating for some value of armature resistance. So for this value of load torque, the motor will operate at this point. Now if you increase the load, what will happen? Your operation will go on, operating point will go on shifting. Is that correct? Yes, or no?
Sir.
Yes.
Yes, sir. Sir, yes, sir.
If you further increase the load, your operating point again goes on shifting. Okay. What is happening? The motor torque is increasing, the load torque is increasing, so the motor torque is also increasing and the speed is decreasing. If you go on increasing the load torque, a point will come when your motor speed will become 0. Correct? And if you further increase the load torque, what will happen? Your crane, instead of going up, will now start going downwards. Okay? Your speed will become negative. Your speed will become negative and you will get IA is equal to V plus E upon R. And you have not made any change to the supply. So your supply is still plus V, it does not become minus E. But because your direction of rotation has reversed, your E has become negative, the minus minus it becomes plus. The armature current becomes V plus E upon R. So here also you will get counter current braking or plugging. Okay, is this clear?
Sir, what you have actually means so actually I have not got, sir.
What I'm saying is that if your load torque becomes such that your motor, you are trying to move the motor in the forward direction, but your motor starts rotating in the reverse direction, then also you are getting plugging or counter current braking without changing the supply. You are not
Yes, sir, yes.
reversing the supply, but you are getting counter current braking or plugging. Okay? Okay, so these are also the speed torque characteristics under plugging. These are also under plugging, these are also under plugging. Okay, you can get plugging.
For this, what actually you have to do means to means reverse the torque for that. What you have actually means done here?
You have not reversed the torque, you have increased the load torque so much that the motor starts rotating in the opposite direction. Torque is still
We,
positive.
we have increased the torque.
Yes. Increase करते गए ना torque को continuously.
Means torque speed
Load torque.
characteristic.
Load torque. This is the load torque. This red color line is the load torque. Blue
So
color
we
line
have
is the motor
we have
torque.
increased the load torque. At one torque means motor torque is less than motor torque will be less than the load torque.
Motor
So
torque is equal to the load torque. This is the operating point.
okay, and then when to reverse the motor torque?
As you go on increasing the load torque, a point will come and the motor will start. When the load torque will be so high that your motor will start rotating in the reverse direction. Suppose you have a crane, you are putting material in the crane. Your crane is, or you have a hoist that is carrying material up from the ground floor to the, let us say, 10th floor. Now on the 3rd floor, you put some material on the hoist, and then you move the hoist upwards. So your hoist is moving at a certain speed. On the 4th floor, you add more material. Again, you move the hoist up. So now your speed will decrease. Correct? At the 5th floor, you add even more material. Now you try to move the hoist up. You put so much material, this much. Now you try to move the hoist up, but the hoist will not move up. Its speed will remain 0, even though you are applying motor torque, but because the load torque is so high, the hoist will not move up. Now at that point itself, if you put more material, if you add even more material on the hoist, your hoist will start coming downwards. Okay? Yes. Okay, think about it. Okay, you'll get it. It's not such a big deal. Okay, I'm moving to the next topic now, and that is speed torque characteristics of series wound DC motors, DC series motor. Okay, any questions regarding this? Anyone?
No, sir.
Okay, DC series motors. Now for any DC motor, the basic equations still apply. What were the basic equations? First of all, V is equal to V plus
V is equal to E plus I.
R, where R is the resistance of the armature circuit.
Armature resistance.
The second equation, torque was proportional to flux
K phi IA.
to armature current. And if you remove the proportionality sign, we get a proportionality constant, that is K. Third equation, the back EMF is equal to
K phi omega.
K phi N.
No, K phi omega.
Okay. But omega is the angular speed of the motor in radian per second. Okay, we can take N also. You can take K phi N also. But then the two constants of proportionality will be different. We'll have to denote them by KT and KB. Okay. If you want both the constants to be same, then in torque we have K phi IA and in E we have K phi omega. Okay, is this clear?
Yes, sir.
So this gives us omega is equal to E divided by K phi. E divided by K into pi. It is equal to V minus IA into R divided by K5. Now the difference here is, in case of the DC series motor, this R is the resistance of the armature as well as the field winding. Correct?
Yes, sir.
Yes.
This R is now the resistance of the armature winding as well as the field winding. Plus, if you add any external resistance, that will also be included in that R. And the difference between the shunt motor and the series motor is that in case of a shunt motor, the flux and the armature current are independent of each other. And you can change the armature current while keeping the flux constant. Whereas in case of a series motor, the flux is a function of the armature current. You cannot change the armature current while keeping the flux constant. If you change the armature current, the flux also changes. Correct?
Yes, sir.
Because the same current is flowing through the armature winding and the field winding. The armature current and field current are same. So the armature current itself is responsible for the development of the field flux phi. What will be the graph between the flux and armature current? So let us say we take flux on the y-axis and armature current on the x-axis. Okay. This is armature current. What will be the relation?
That linear relation up to some extent.
Linear.
And after that, saturation.
Just not getting it. So you get something like this. I hope you are getting it, what I am trying to do. And this curve is not coming properly. So you get this type of curve. Okay? It will be not exactly linear, but you can approximate it as a straight line up to a certain point. And after that, the saturation sets in. Okay? After this point, we can say that it is after this point, we can say that the armature circuit or the field circuit becomes saturated. It becomes saturated means even if you increase the armature current, there will not be a correspondingly equal increase in the flux. Okay. And in fact, after a particular point, when the magnetic circuit becomes completely saturated, even if you increase the field current, the flux will remain constant. Okay. So because the flux, if we consider saturation also, we cannot write an equation between the flux and the armature current. Correct? There is no exact mathematical equation that can be set up for the magnetization curve. Is that correct? Consider the entire characteristic. There is no exact mathematical equation for the magnetization curve, or you cannot write a perfect or a simple equation between the flux and the armature current. Because in that case, it will be difficult for us to draw the speed torque characteristic. So what we do is we assume that the magnetization characteristic or the characteristic between the flux and the armature current is a straight line. Okay, that means we are neglecting the saturation. In that case, we can say that the flux is proportional to the armature current, or flux is some constant A multiplied by the armature current. Correct? Yes or no?
Yes, sir.
In that case, the motor torque, that will be equal to A multiplied by phi. Phi is A multiplied by IA. It becomes AA multiplied by
IA square.
I will drop the subscript now. I means I. The torque is equal to Ka into I square, or Ia is equal to under root of torque divided by Ka. Torque divided by Ka, everything under root. Okay, so if we substitute this in this equation, we get omega is equal to, first of all, V upon K phi. V divided by K phi. Phi is A multiplied by Ia minus Ia into R divided by K phi. Phi is again K multiplied by I. Okay. So I and I will get cancelled. Correct? And we are left with P upon KAI minus R upon KA. Or this I can be written as under root of torque divided by under root of KA. Correct? It becomes K divided by KA divided by under root of KA will be under root of KA. I don't know where the under root is. Where the under root sign is in this.
So fourth one, sir.
This one?
No, sir. This side. So below, sir. Second line, second one. Yes, sir. Second line, second one.
Second line, second one. Okay. So the first term will become V divided by Ka upon under root of K will be under root of K multiplied by under root of torque minus R upon V. Correct. This is the equation for speed. Or this can be written as some constant capital A. And what is the value of capital A? Is V divided by under root of Ka. That is capital A divided by under root of torque minus some constant capital B, where B is R upon Ka. Correct? So the equation defining the speed and torque. So the question is, how will be the speed torque characteristic now? Save this. those are good characteristics. There's so much. The class so silent today. Even Priya Malhotra is not saying anything today. There's some problem. Priya, are you there in the class?
Yes, sir. Yes, sir.
Yes,
Yes,
sir.
sir.
Okay, good. Okay. So how will be the characteristic? ये किसकी इक्वेशन है? Whose equation is this? Y is equal to a by root x minus b. Whose equation is this? Is it the equation of a straight line?
Sir, hyperbola.
Hyperbola, yes.
It is the equation
Yes,
of
sir.
a
Not
hyperbola.
not straight line, sir.
That means
So non-linearly decreasing.
So the origin is shifted, sir.
this is the equation. है ना?
Yes, sir.
For small values of torque, the speed is high. As we increase the torque, the speed decreases. है ना? If torque becomes zero, the speed becomes infinite. Okay? This line is going to touch the y-axis at infinity. Okay? This line is going to touch the y-axis at infinity. Concept of asymptote. है ना? You remember asymptotes? Control system, root locus.
Yes, sir. Yes.
So this characteristic has the y-axis as its asymptote. Okay, so these are the speed torque characteristics of a DC series motor under under motoring conditions. And the speed is inversely proportional to the square root of the torque. For small, as you go on decreasing the torque, the speed goes on increasing. If the value of torque is less, the value of speed is high. That is why a DC series motor should never be started under no load. Because if the load torque is zero, the motor torque is zero, the speed tends to go to infinity. In actual practice, it will not become infinite, but it will become so high that the motor will not be able to withstand the mechanical forces. Okay? The shaft might break or whatever problems you might face. That is one of the reasons why we go for compound motors. The purpose of compound motors, one of the purposes of the compound motor is to limit the no load speed of the DC series motor. Okay? Clear? Any questions regarding this characteristic?
No, sir.
No, sir.
So let us now come to, if you change the value of R, what will happen? Change the value of R. There is no R here in the first term. The only R is there in the second term. This is R upon Ka. If you change the value of R, what will happen to these characteristics?
Downwards direction, sir.
It will move, sir.
Yes, down.
It will move downwards actually. Minus signification is the minus sign. Okay, so if this, I say that this is the natural characteristic, and these will be the characteristics with external resistances. Okay? Of course, the characteristic will not touch the y-axis. Okay. Any questions regarding motoring?
So compound motor means so please sir explain the compound motor, sir, once again, sir.
Compound motor means it has two windings. One is a series winding and one is a shunt winding. Okay. The main winding is the series winding. The purpose of the shunt winding is to impart sort of shunt characteristics to the series motor. Okay. Limit the no load speed of the DC series motor to a finite value.
Means no load speed of DC series motor is very much high. So here what actually
This
means
will be the characteristic of a compound motor. similar to a DC series motor, but this is your no load speed now. It is not infinite. It has a finite value. Okay. Why it has a finite value? Because of the shunt winding. Okay, any other question? There are no more conditions, then we'll move to braking. Okay. Now, how do you get regenerative braking in a DC series motor? Regenerative braking. What were the conditions for regenerative braking? IA is equal to V minus C upon R. IA is equal to minus C divided by R. So there were two conditions. If the supply voltage is constant, both the conditions are valid if the supply voltage is constant. So the conditions were E should become greater than V and armature current should become negative. Okay. So how do you get regenerative braking in a DC series motor with the supply voltage constant? How did you get it in DC shunt motor? The load caused the motor to run at a speed greater than the no load speed, because of which E became greater than V, and armature current become negative. So is that possible in case of
So by decreasing the load,
by decreasing the load,
means
E will become greater than V? Anyone? Vikram? Badal?
Yes, sir.
How do you get regenerative braking in DC series motor? How can you make E greater than V in DC series motor?
It's not possible, sir.
Yes.
Not possible. Yes.
Who gave that answer? Name.
Sir, if we
Me,
can
sir.
connect the what shunt means field winding
Sir.
shunt.
I'm asking for name. Who gave that answer?
Shubhajit, sir. Shubhajit,
Nobody. So the right answer is that you cannot get regenerative braking in a DC series motor, because if you increase the speed, and E is proportional to flux and speed. If you increase the speed, E increases, and as soon as E increases, the value of armature current decreases, the value of flux decreases. Okay? So these two, in case of a DC series motor, if you increase the speed, the value of flux decreases. So E is almost constant in case of a DC series motor. Okay? So you cannot make E greater than V. Clear? Clear?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
You cannot make E greater than V in case of a DC series motor, and hence regenerative braking is not possible in case of a DC series motor. So you can get either dynamic or rheostatic braking, or you can get plug-in counter current braking. What will you do for rheostatic braking? It is simply remove the supply and connect the rheostat there. Yes or no? You simply remove the supply and connect the rheostat there. Yes. How will you get rheostatic braking? Subhajit, we simply remove the supply and connect an external rheostat.
Yes. If we disconnect the supply, speed will be high, sir. In that case.
What
So
we have to do
resistance
is, yes,
always, sir, one external resistance is always there with the
Yes, sir. You have to
and
connect an external resistance in that case.
external resistance has to be there, plus something else also.
So you are saying, sir, in the case of DC series motor, you are saying that if we will increase the E, then IA will decrease. IA will decrease, then you are saying that field will decrease. Field will decrease means what is the meaning of that? Means
Flux will decrease.
flux will decrease. Then what will be happen? Then what will happen?
Then your E comes back to its original value.
Yes.
E comes back to its original value. E again decreases. You increase the speed, E increases, flux decreases, E again decreases. Okay. Yes.
So yes, sir. Yes, sir. Yes, sir.
So where were we? In case of rheostatic braking, do we simply remove the supply and connect an external rheostat, or something else also has to be done? Yes, someone. Very simple question.
so we have to take out the supply and connect an external resistance.
What will happen then is,
Sir, as soon as we disconnect the supply, then the speed will be so high, it will damage the DC motor. So we cannot disconnect the supply.
the supply will turn off. And it will turn off.
That means we can step
Speed
by.
will increase if you remove the load. No load, the speed will be very high.
Sir, we can connect external resistance across the load and we can disconnect.
Disconnecting the supply means you are making it open circuit. And the armature circuit, the field circuit, everything becomes open because the motor will turn off. But you cannot control the speed. If you want to control the speed, you have to allow current to flow through the armature circuit. And for that,
Yes, sir.
you
Can
have
we
to short
connect?
circuit it. You have to complete. You have to keep the circuit complete. So you can short circuit it, but then the current will be very high. Yeah. So you connect an external rheostat. But still, you cannot, if you want fast braking, what you have to do is, you have to remove the feed and maintain the flux constant. Okay? You have to remove the field winding, keep the supply across the field winding as before, so that your flux remains constant. And the armature circuit, you have to connect an external rheostat. Is that clear? Yes.
Sir, please repeat.
If you want fast and controllable braking, you have to maintain the field flux constant. So you'll maintain maintain a supply across the field winding so that the field flux remains constant. And the armature terminals, you will connect an external rheostat across the armature terminals.
Okay.
Is that clear now?
Yes, sir.
Okay. So armature terminals, you will connect an external rheostat. Let us say this is that external rheostat, and the field winding you'll still maintain the supply. Okay. So how will be the characteristics then? Will they still be hyperbolic, or they'll be parabolic, or circle, ellipse, straight line?
So it will be same as separately excited DC.
Yes, correct. Will be same as
So
the
y equal to
speed torque
minus mx plus
characteristics. This one, speed torque characteristics of a separately excited or DC shunt motor. Okay. Clear? Because the conditions are same. The rheostatic braking is same for DC shunt motor as well as DC series motor. The speed torque characteristics are same, passing through the origin. Okay?
Yes, sir.
Yes or no?
Yes, sir.
Yes, sir. Yes, sir. Yes.
Okay, so suppose this is the load torque. This is the load torque characteristic. Okay. So, and then in steady state, what is happening? This is the operating point. This is the operating point when the motor torque and load torque are same. Now to break the motor, what we are doing, we are disconnecting the armature from the supply. We are maintaining supply across the field, but we are disconnecting the armature from the supply and connecting it across an external resistance. So instantly what happens? The speed cannot change. The speed cannot change, but the torque reverses. So instantly it will move from this characteristic to this characteristic, and with time the speed will go on decreasing until it becomes zero. Okay, clear? Yes? Yes or no?
Sir.
Yes, sir. Yes, sir.
Yes, sir.
So this was rheostatic braking or dynamic braking of a DC series motor. What happens in plugging? Plugging, you maintain the supply as it is, but you reverse the armature. You do not reverse the supply. If you reverse the supply, then your armature current as well as field current, both of them will reverse. Because your motor torque will still remain positive and it will still act as a motor. So you do not reverse the supply. You keep the supply as it is, but you reverse the armature terminals by keeping the field terminals same as before. So that your flux still remains constant, but your armature current becomes negative. In that case, these are the speed torque characteristics under counter current braking or plugging. Instantly it will move from the first quadrant to the second quadrant. It will move like this, and when the speed becomes zero, you have a negative torque, so that if you do not remove the supply, the motor starts running in the opposite direction. And as we have seen in case of DC shunt motor, this is also one of the possibilities of plugging or counter current braking. If you increase the load torque to such a high value that the motor starts running in the opposite direction, then also you can get counter current braking or plugging. I'm stopping the recording.